Good evening, students. My name is Shashank and we are doing a crash course on chemistry for the upcoming JEE exam. And today is our 42nd day. We have started the chapter that is organic compound containing nitrogen. The first part was of preparation and basic structure. So, it mainly focused on the preparation methods and the structure of the amines. Now, today we will focus on their preparation and reactions. So, this is the syllabus that we have. Okay. So this is the detailed topic to be covered. So first one will be basicity, then acylation, then carbylamine reaction, Heisenberg reagent. Then we will see some reactions with nitrous acid, electrophilic aromatic substitution, reaction involving displacement of nitrogen, then reaction involving retention of diazo group coupling reaction. So these are the topics that we will be seeing today. So if you see the overall weightage, so average of 1 and 2 questions come from this chapter, which is of 4 to 8 marks. Now let us start our chapter. So first we will start with the basicity. So we have seen that nitrogen is a sp3 hybridized molecule in which this R can be, there are three R's here. This R can be anything like alkyl group. So one of these must be an alkyl group, then and then only it can be called amine. Otherwise, if all of the three alkyl group are say hydrogen, then it is called ammonia. So this R can be alkyl group or hydrogen, and this R dash, suppose it should be alkyl only. So this was the basic structure of say amine we yesterday looked upon. Now, if you look here, it is a lone pair that is present. So it is a kind of Lewis base that can donate lone pair. So if you see a comparison between alkyl amine and ammonia, so simple alkane and amine ammonia, then this alkane amine is much more basic than this amine. Why is it so? Because suppose this is the this is the protonation of this alkyl amine and protonation of this ammonia. So it will give an intermediate that is positively charged. So both of this will give two intermediates. Now if you look at the stability of this intermediate, all of the three substituents, that is this three hydrogens, are same. So here we are taking a primary amine. Why primary amine? Because the nitrogen is attached only to one alkyl group and other two are the hydrogens. Now if you look at this say structure, you can see very clearly that this R group is present here, which is showing a kind of plus I effect, or you can say positive inductive effect. But in this here carbocation, there is no such group that is present. So all of these three are hydrogen, and hydrogen's plus I effect is smaller than this alkyl group. Not due to this reason, the say conjugate acid or that is formed from this base is stable as compared to the ammonia for the alkane amine. Now if you look on the specific, that is alkane and amine, and compare the basicity of all of those in aqueous medium. So if something is base or something is acid, it is in respect to something. So keep this in mind that nothing acidity and basicity are not an absolute terms. They are somewhat relative terms which is related to something. So if you dissolve this amine to water, then it will show its basicity then and then only. Pure amine, so suppose you are taking a pure solution of any amine, and that should be pure, means suppose we are taking methylamine, then it will show no traces of basicity or acidity. But as soon as you dissolve it in water, it will react with the water molecule and show its basicity. So if we consider the basicity in aqueous solution, then for the ethyl one, it shows this order, that is, this one is 2 degree, 2 degree, 3 degree, and 1 degree. Now if we look upon this methyl case, so the substituted thing is methyl, so it is first 2 degree, then it is 1 degree, then it is 3 degree, and this ammonia is at the last. So this is the basicity order in the aqueous medium for the amines and ammonia. Now you will ask that how you have decided this one. So it should not be this, because you are saying that okay, that alkyl group is say stabilizing this one. So much more number of alkyl group means much more stability. So third should be at the first one, means the most basic one, then the second one, then the first one, and the same should be true for this ethyl and methyl group also. So what is the factor that is changing the overall result? So you are dissolving it in water. The first one is inductive effect, of course, that is affecting this basicity. But the second factor is the solvation effect. So what is solvation effect? So as soon as you dissolve this ammonia in water, then it is, say it is surrounded by water molecules, and it creates a circle of water molecules. Now due to this, some kind of steric hindrance is induced in that tertiary amine. So this point is clear. So as you dissolve this ammonia into water, we have seen earlier that ammonia is, or amine is, soluble in water because it is forming hydrogen bond with water molecules. But it has an adverse effect also, that it cannot just the third degree amine, which is dissolving in water. So upon losing its hydrogen, it forms the kind of hydrogen bonding interaction with all the water molecules, but it also creates at the same time some kind of steric hindrance. Due to this reason, the stability of this thing, this conjugate acid, becomes less. Now, so sir, to this reason it is placed at second in case of ethyl and placed as last in place of methyl. So this is the case of basicity of amine in aqueous medium for the say amines. Now you should remember this order. For ethyl it is 231, and for methyl it is 213. So this thing is important. At last is the ammonia. Now overall these three effects are deciding the final sequence of this basicity. Next, if we compare this ammonia with aryl amine, then ammonia is more basic than aryl amine. And what is the reason? So if you consider aniline that is present here, or the aromatic amine, so you can see very clearly that this lone pair is going into conjugation throughout the ring. Due to this reason, they are less available. Okay, so they are less available for donation. So they are kind of weak Lewis based as compared to ammonia. And second reason is that, so if you are just seeing the stability of this aromatic amine and comparing it with this anilinium ion that is formed upon protonation, you can see very clearly that the number of resonant structure is decreasing by a factor of 3, sorry, factor of 3 not, by a difference of 3. It is having 5 resonance structure, and it is having 3 resonance structure, sorry, 2 resonance structure, this anilinium ion. That is why it is more stable. So this one is more stable. Now due to this reason, it avoids from going to this structure to anilinium ion structure. And second, the lone pair that is present on nitrogen is delocalized over the ring. So if you look at the starting page means, suppose this is the reaction that we are having. So two things we see. So this is our conjugate base H2O. It is going to conjugate acid. Now if you look upon this thing, then you will see the availability of electron. But if you are seeing the conjugate acid that is formed, then you will see its stability. So more is the stability of conjugate acid, more the base will be strong, and more will be the availability of the lone pair or the electron. You can say more is this. You can say more is this basicity. This factor, this stability factor, is much more emphasized because it is applicable to all of this, while this availability of electron is only applicable to Lewis base kind of thing. So this is a much promising factor that should be considered. So we can see that the stability is reduced. So this is clear cut here. So this was the basicity. Now let us see a wide variety of amines and let us compare their basicity. So first one we have alkyl amine, so which is the most basic one of all the amines. Then comes the aryl amines, so all the aryl amines are in the second part. Then comes the heterocyclic aromatic amines, which is in the third part, and last we have the amides. Okay, so this is the overall table. So why is it so? The first 2 points are clear. We have made it clear that the aryl amines lone pair are going into resonance, and also their aniline amine are not much more that stable. And second, if we consider it with this or compare it with the heterocyclic aromatic amines, which is this one or this one, so if you can see here that it is aromatic, so if you consider both the structure, they are kind of this. So why this is less basic? Why? Because it is sp2 hybridized. So it will have more s character. More s character means this lone pair are present in more electronegative orbitals. So it will be difficult for donation. So this is the hierarchy that you can consider for the less basicity of this nitrogen lone pair or nitrogen. Now, if you compare this one, you can see that this is a 4n plus 2 pi system, which is aromatic in nature. And this 4 and 2 pi also include this lone pair, because if you just exclude this one, it will be anti-aromatic, or sorry, you can say non-aromatic, because it will have no conjugation. And for that reason also we are not considering this lone pair, because if we consider this one, it will be anti-aromatic. So we do not consider this lone pair as a part of conjugation of this ring. Similarly, we have to consider this lone pair as a part of conjugation of this ring. Okay. Now, since this lone pair is going into conjugation to keep the aromatic, so lone pair is in conjugation. Now, due to this reason, this both are lesser. The less, you can say this both are less basic. Okay. Now the last one is the RCONH2. So if you consider it with RCONH2, then of course it is less basic, because it is going into conjugation like this. And most of the time, this lone pair lies on this. Okay. Okay, the equilibrium is shifted more towards this one. You should not be disagreeing with that one. But most of the time it is upon the oxygen as compared to this one. Due to this reason, it has a less basicity, or you can say least basicity. So this is the reason for the order that we are having here. Now, if we go more deeper into this order, then you can see that this is the most basic one. Okay, so this is the most basic one. And it is present in this form. So this is the most basic one with a pK value of 11.1. Then of course we have the 2 degree, then the 3 degree and the 1 degree. I have ordered that is I have told you earlier also. Now if you consider this at this 4 here, that are present, then OCH3 substituted, so it is OCH3 substituted aniline. So this O group is present in para, so it will donate its electron will donate its electron to plus M effect because this group is also para directing. Then we have the para CH3. So para CH3 also donates electron. How? By plus I effect and through plus H effect. How plus H effect? So this is the hydrogen that we are having. So it will go like this and it will increase the electron density. Then we have the normal C6H5CH2. Then we have our para NO2. So why para? Because right, why it is the least one, least basic among all of those amines, aromatic amines, sorry, anilines, because of this nitro group that will show your minus M effect and will decrease the electron density on this nitrogen. So this is the reason for this order. Now this reason should be clear. So why is this one is more aromatic, this one? Because its lone pair are of course not there in present in the sp2, but they are not going to the conjugation, while in this case the lone pair are going into conjugation for the aromaticity factor. So this one is the least basic. So you should remember this point, this that if any lone pair that is to be considered as the factor deciding the basicity, and if it is going into aromatic ring, then it will be the least basic among all of those. Okay, so this should be kept in mind. Now at the last we have the amide, that is to be the uh, least basic of all of those, having a negative value of pK. So you can look upon this value and decide that okay, so this is why this is least basic, because none of these have a negative value of pK except this amide. So this is the overall order of basicity. So you can refer this table again and again and find your answer to every basicity question. Now I can have a third overview here also. Now if you look upon this one, okay, or suppose you have a kind of structure like this. Now this can be substituted by any functional group, no matter, but it will be the most basic one of all of those. Why? Because it will have a conjugation and will have a negative charge on this, say this nitrogen. So it will be the most basic one. So if you see anywhere this kind of structure present, then consider that one as the most basic one. Okay, so this was all about the basicity. Now we'll see some reactions of these amines. So the first one is the acylation. So what is acylation? So it is basically introduction of this group to your substrate. Now how it will happen? So it can be done by using any primary secondary amine, primary and secondary amine and aliphatic amine upon reaction with acid chloride and hydride and esters. So if you use any of these three and react it with this, say, primary and secondary amine in the presence of a base, so you should be using a base that can abstract your HCl, then you will get your, say, this amide. Now here are various reactions that are put upon. So the first one, we are using acyl chloride in the presence of base, so this amine react with it and give you this amide plus HCl. In the second reaction, what we are using is we are using a anhydride. So this is the anhydride group. Again we are using a amine, but we are not using any base because this is a good nucleophilic center. This will give you a carboxylic acid plus your amide. And the last option that we are having, or the last, you can say the last example that we are having, is we are using a ester. And we are using our amine again. Now in this case we are using a primary amine. Then we will get this amide again and your alcohol. So you should remember the side product as well. So these three side products are also important for your exam point of view. That this acyl chloride gives you HCl, benzene amine gives you this carboxylic acid, and ethyl acetate gives you this methanol. Okay, so this is acylation of these amines. Next, we have a carbylamine reaction. So it is kind of test also for the primary amine which is used. Okay, so what do we do is we take RNH2 and in presence of CHCl3 and KOH, a basic sin. So if anyone asks you that what is the intermediate here, then you can say, so I'm not giving the whole mechanism, but for just for knowledge, it can be said that it is involving formation of carbene during this reaction. So we heat this mixture. So this mixture is heated and we get the reaction as this one, which is RNC, and it has a fall smell. So sometimes in laboratory language we also say as it has a rotten egg smell. So this is the terminology. So it is often used in the labs. So this is the carbylamine reaction that is used for the identification of a primary and aliphatic amine. So it should be primary aliphatic or aromatic. So what do I mean by this? That okay, this can be this one aniline, or it can be this one. In simple, this R can be aliphatic or aromatic, and it is not given by secondary and tertiary amines. So it can be used as a distinguishing test. So suppose you are giving two amines. So first one is primary and the second one is secondary. So if you perform this carbylamine reaction and if you get a fall smell, then you can say certainly that it is the primary amine. Otherwise, it is a secondary or tertiary amine. Now the next same thing is written here. It can be used for the detection. Next we have this Hinsberg test. So it is also for primary amine only. So this is called as Hinsberg reagent. Okay, this is thionyl chloride. So we react it with this primary amine and we get this thing here, which is a N substituted, or you can say N-ethyl benzene sulfoamide, that is soluble in alkali. So it is soluble in alkali. So you can be asked a question that okay, you are given a amine and it is, and if or you said that you are given a compound and it reacts with this Hinsberg reagent and the substrate is soluble in alkali, then you can say that okay, that must be a primary amine. Similarly, you can have another example in which we have a secondary amine, but the thing about this say this thing is that it is not soluble in alkali. It is not soluble in alkali. At last, we have the tertiary amine that do not react. So it can be used as a distinguishing test. So if you are given a mixture of primary, secondary, and tertiary, you can easily say that okay, so this one is primary since it is react with the Hinsberg reagent and gives you the solubility in alkali. Second, if it is secondary amide, it react with this Hinsberg reagent but this does not is soluble in alkali. Third one, so if it is not reacting with this Hinsberg reagent, then it is of course a tertiary amide. Next, we have another some important reactions, that is reaction with nitrous acid. So this is the most important reaction of all in this chapter. That is diazotization or reaction. So it can be done for both for aliphatic and aromatic. So this aromatic one is a more descriptive one. So we will see later on many reactions that is based upon this diazotization of this aromatic ring. So if we do the diazotization of this aliphatic ring, it will give you a complex that is not stable, and as soon as it is bring in contact with water, it gives you alcohol and 2NHCl. So it form a kind of adduct here, and it does not require temperature also. Now, if you perform the same reaction with this aniline, it will give you diazonium chloride, or you can say benzene diazonium chloride more specifically, plus NaCl plus H2O. Now, secondary and tertiary amine react with this nitrous acid in a different manner. So they do not give this thing because it is not possible for them, of course, because this N is satisfying gas valency using N2 and Cl minus. So this does not react with secondary and tertiary amine in the same manner. Next, let us have a look at some aromatic electrophilic aromatic substitution of this aniline. So like this OH, or you can say phenol, it is also giving a tri-substituted ring. So 3 bromine are present at this ring if we just bring it in contact with this Br2H2O. Now how we can reduce it is that we can just substitute this thing with this acetate ion initially. So what does it do? It deactivates this ring to some extent. Why? Because now this lone pair is also going in conjugation with the carbonyl compound. It is simultaneously going, sometimes it is going to this place, sometimes it is going to the ring. So initially it was only activating the ring. Now by some of the electron density is shifted to this carbonyl group. Of course, we use a base to substitute it with acetic anhydride. Okay. Now, if we react this with Br2CH3COH, now we'll get a para as the major product. And at last, you simply do the hydrolysis and you get your required thing. So this is the bromination of aniline. Now, if you do the nitration of this aniline, then you will get three products, and two at the comparable amount also, and third at the least amount. Now, how do we do the reaction or proceed the reaction that we do not get any kind of impurities, or you can say we do not get any kind of mixture? So we do the same thing, that is we substitute this hydrogen with this anhydride initially, and then we do the sulfonation to get our para product in major. Now when you get your required reagent, you just have to remove this COCH3 by H. So you do it by hydrolyzing. So this is the final product. So this is about the electrophilic aromatic substitution, that is bromination and nitration. Now if you look at the sulfonation, so if you use this H2SO4, it will not give you simply your sulfonated benzene ring, it will give you an HSO4, this kind of substrate. Okay, so it will give you this kind of substrate. Now you will heat it again to give your NH2 and sulfonated benzene. Okay, so this is about the sulfonation. Now this you can say that the electrophilic aromatic substitution is not that simple in case of aniline. Next we have this reaction involving displacement of nitrogen. So we will see various reaction of this diazonium salt. Okay, or you can say in specifically benzene diazonium salt, diazonium chloride. We will see various reactions of it. So these are the set of reactions that are called as Sandemeyer's reaction. So what do? Is we take various nucleophiles. So first we are using cupric chloride, cupric bromide, cuprous cyanide, and then we react it with this benzene diazonium chloride to get our required substitute. Okay, so first we are getting a Cl, Br and Cn. So you can see it is a very important reaction. We can simply introduce various functional group by only using initial substrate as aniline. Now this is Gutterman-Koch reaction, Gutterman reactions. So what do we take? We take different substance here. We use a copper, we will not use a copper salt here. So instead we use a acidic condition in presence of this copper. But our substrate will be same, that is ArCl and ArBr, this N2 and your COX. So this is the reaction involving nitrogen. So some more reaction if you want to see, you can see here. So first one, it is not easy to substitute with iodine. So what do? We react it with potassium iodide to get our ARI in place of Cl plus N2 plus Cl minus. Sorry. Again, if we react it with HbF4 and heat it, you will get your fluoride benzene. So it is an important example. Now, if you react it with H3PO2, that is this is an acid and water, you will get your simple benzene. Or else, if you treat it with C2H5OH, this one, then also you will get your simple benzene. Next, it will treat it with water. You can get your uh, phenol here. At last, we have this reaction in which first we treat it with HbF4 minus and then we treat it with nitric acid to give our ArNO2. So we are again treating it with NaNO2 presence of copper. Okay. So this is the introduction of this NO2. So you can use this process also for the production of this nitrobenzene. Now let us see some of the coupling reaction that we have here. So these are some important coupling reaction. So the reaction involving retention of diazo group. So in all of this reaction, we get back our diazo group here. So this is the diazonium salt that we are having, and we're reacting it with phenol. So what do we get? We get para-hydroxybenzene. And what is special about this compound? That it is orange dye. So it is used as a dye also. Plus Cl minus and H2O. Second, again we are doing this same reaction, but we are doing it with the help of a NH2, that is aniline. So these both are coupling reaction. We are coupling this molecule with this molecule in the first one, and in the second one we are coupling this molecule with this one. Now the thing here to notice is that the first one is done in presence of base and the second one is done in the presence of acid here. Okay, so this is important about this reaction. So we get this ring that are phenyl, that is having two phenyl ring. The first one is orange dye, the second one is yellow dye. So this aniline gives you yellow dye and this OH gives you orange dye. Now again, some important points I have to notice is that the azo products are often used as dye. So you can be asked in the question that upon a coupling reaction you get something that can be used as dye, then you can guess the product. Now the second most important point is that this is nothing but a electrophilic aromatic substitution reaction. So if you are told that in which place, why you are getting at this place or at this place, because it is a electrophilic aromatic substitution and this nitro group or the oxygen group is just activating this ring at ortho and para position. That is why we get this at para position, or you can say the coupling reaction at para position. So this was all about the nitrogen containing compounds. So we moved from different preparation method to chemical reaction, and then we moved to diazonium salt, the most important part of this nitro group or nitrogen group. Now let us see some questions. So I have to put some interesting question for the practice. So let us do these questions. So the first one is says that we are taking a fluoronitrobenzene. Okay, so we are taking a fluoronitrobenzene and plus we are taking something CH3 to NH. Then in the you in the presence of DMF and heat. Okay, so what should be the product A? Then this A is reacted again with this FeHCl that will reduce the OH into say your CH3 group. Sorry, this OH will be reacted in this case. Now NaNO2 plus HCl, that is N2 plus and Cl minus. Okay, and at last you get your H2Ni. So you will get at this position. Now what can be the say predicted product? So how you can proceed this reaction? So it is the solution of this one. So what do? Is we simply do the electrophilic aromatic substitution of this fluorine group. So we are substituting this N with this one. Now in the second, we do a NO2 reduction using FeHCl NH2. Then we do the diazotization reaction N2 plus Cl minus, and at last we do the reduction to get our NH2 here. So this is the overall reaction that we are having. Then we have the second question. The best method to synthesize this M-dibromobenzene is using by the reaction. So which reaction can you use? So if you use this benzene, you will get your bromobenzene. So this reaction you know. Now if you use this aniline here, then it will be brominated at 3 positions. Okay, and upon HUNO and BR, it will give you somewhat this kind of product. So it is not your M-dibromobenzene. Then we can have a nitrobenzene also. Okay, then nitrobenzene is reacted with HNO3 H2SO4. So you will get your aniline again. Okay, sorry, you will get a sulfonated product because this is a kind of sulfonation reaction, and you will get this at meta position. Then we have this FeHCl, so it will just reduce this thing to give you NH2. Then again HUNO, it will give you this N2 plus Cl minus, and then bromine. So it is also not the required answer. At last we have this bromobenzene. So simply we are taking a bromobenzene here. We're reacting with HNO3 and H2SO4 to get our SO3H at meta position. Then we are reducing this thing. Okay, we are reducing this thing to get our NH2 again, and we are again reacting it with HONO and CuBr to get our Br here. So this can be your answer, the last one. The same thing is written here. So we are using a different reagent, sorry, with a NO2, then fuming HNO3 and H2SO4 to get our nitrating mixture. Again we just reduce it, then NH2 and H2H both positions. Then we introduce this HANO to do the diazotization. Okay, and at last we use the CuBr to get meta-dibromobenzene. Next, the correct order of basic strength of all of this. So you know very well that the amide are the least basic one, but all of these are amide except this one. So this is the most basic one of all of this. So 4 is this one. So you can simply say that this is the answer. Okay, so same thing is written here. Now this question, what does it say? So you are taking conc H2SO4 and heat, then you are getting here ortho and para isomer. Of course, it is sulfonation reaction. So you will get two types of isomer, which is ortho and para. Then the ortho isomer, that is this one, CH3, is reacted with this PCl5. Okay, so you will get your SO2Cl. Then you will react it with NH2 to get here NH2 and your CH3. Again, we just aqueous KMnO4 gives you COOH. And now when we heat it, this both of this say couple with each other to give you this one. That is B. So B is the correct answer. Okay, so this is given here also that B is the correct answer. Next, the fifth question and the last question that I will be solving today. Then you will solve the rest of your by self. So it is a dehydration reaction. So simply it will form a N2 plus and Cl minus, and you know that it can give the electrophilic aromatic substitution. We have seen it earlier also. So it will give the electrophilic aromatic substitution here. So this is the correct answer. So it will just attack here, and this both will combine like this to give you this as the answer. So this is the correct answer. Now less of the question, I will just give you hints, and if you want, you can solve it. Which of the following reaction belongs to electrophilic aromatic substitution? So coupling reaction, yeah, it is. Bromination reaction, yeah, it is also. Diazotization, so it is not a electrophilic aromatic substitution. So both A and B is the correct answer. Next, we have this one. So it is a very long question, but let me remind you one thing, that this kind of transformation are very interesting to solve. So first we are taking the nitrating mixture here. So it will nitrate at this part. So same thing is done here. Then what we are taking, we are reducing it. So we will get a aniline. Then we are doing the substitution. So we are taking acetic anhydride. So it will get substituted. So NHCOCH3. Then we will do the bromination. So we will get a orthobrominated, orthobromination. Then H2O and H plus to remove that group. Then Na2 and HCl to again diazotize that NH2 plus, N2 plus and Cl minus. Then H3PO2, which will remove this group. So if you want, I can solve it. It's a difficult one. Okay, so how it will solve? So first we have this CH3. So what will happen? It will nitrate this thing using nitrating mixture. So what we will get? We will get this para-nitrotoluene. Then what is being done? We are using a reducing agent, that is FeNH plus. It is similar as H plus or HCl, you can say anything. Both are similar. We just have to create a basic condition. So it will get reduced and give you this NH2, that is aniline. Then next what we are doing is we are introducing a anhydride group. So what will happen in the next step is that, so I'm just inverting this compound. It will look like this, and CH3. Then we are doing this bromination. So it will give you a para substituted one. Then we do our hydrolysis to simply remove this group as a whole. Bromine here also, again CH3. At we last we do the diazotization and we remove using H3PO2. Then finally you will get it as CH3Br. So this is the final product that we have. So this is the correct answer, that is C1. Next, what we are doing is we are taking again NaNO2 HCl. Okay, so what will happen? So at 0 degree Celsius we are doing this reaction. So NH2, what will happen? This NH2 will again give you OH. So here is this OH, OH, OH and OH. So which will be the product? You have to decide by yourself. So you have to decide the you have to decide your stereochemistry. So let me give you a hint. There is a kind of retention of this stereo center. So you should remember this point, that this diazotization involves retention of the stereo center. Next we have this question. So it is a previous year question. So what does it say? So we are just diazotizing this group to N2 plus and Cl minus to get our D. Then we are reacting with the COCN and KCN. So we will get here CN in place of this. Okay. So this is the correct answer. At last, we have this question. So I'm leaving it to you. So I have told you about basicity. So you have to see the basicity of all of the reactions. So this was for today's class. Thank you. So if you want, you can ask question.